So today we're looking at ionic solubility and solvation, which is following on from looking at the three different intermolecular forces. What were the three intermolecular forces we've discussed? Dispersion, dipole-dipole, and hydrogen bonds. And that's in order of relative strength in general. We understand the three. We understand all the different factors that affect those intermolecular forces. Today we're going to look at. We've also looked at how those intermolecular forces affect the boiling point of materials. Today we're going to look at how those intermolecular forces will affect the solubility of materials and a solution's ability to dissolve something, which is what solvation is. So, from the syllabus, dot points, we're looking at the observable properties. Solubility is the one, can be explained by considering the nature and strength of intermolecular forces within a covalent molecular substance. So, let's start off by looking at solutions. So solutions are when we mix two substances together. It's a homogeneous mixture is the result, and one phase dissolves in another. So what you're doing is you're breaking the substance down into its molecular parts. So in the case of here, we've got glucose molecules and water molecules. We've got a glucose crystal in its crystal lattice, and the water is going in and breaking the bonds between the glucose crystal lattice, and the glucose crystal lattice is breaking the bonds between the water molecules, and we're separating it all out so that we end up with glucose molecules and water molecules homogeneously mixed through the solution. The particles are obviously on the molecular scale, so they're too small to be seen. And that's why it's a homogeneous mixture, because you end up with pretty much the same material wherever you go. So it's not an inhomogeneous mixture where sand and gravel mixed together would be an inhomogeneous mixture. So solution is, in this case, the solution is a homogeneous mixture of glucose molecules and water molecules. So that's when we form a solution. The other example, when we may form two different substances together, if they're insoluble, then we end up with a heterogeneous or inhomogeneous mixture where you still have two phases. So in this case, when you mix oil and water together, doesn't matter how much you mix it around, stir it around and so on, you will end up with little droplets of oil inside the water, and if you wait long enough, all the little droplets of oil join back together again, which is why whenever you go to put your salad dressing on your salad, you have to give it a good shake, because the oil is separated out of the water, because the oil doesn't dissolve in water. So in that case, your salad dressing is a inhomogeneous or heterogeneous mixture. You'll remember the terms solute and solvent. Solute is what we're dissolving, and solvent is what is doing the dissolving. Sometimes it's not always obvious which is which, because sometimes they're dissolving in each other, effectively. So solute-solvent kind of works well when we're dealing with a solid, which is usually what we're adding to the liquid, and the solid is the solute, and the solvent is the liquid. But when we get two liquids that we're adding together, it's not always as clear. And the example here is the idea that air is a mixture. Air is a solution. You've got nitrogen, which is the largest amount, but it's not normally referred to as a solvent, and oxygen being the solute. Okay, so that terminology is generally used for liquid solutions. Okay, so when we're forming a solution, we have to rearrange the bonds in the substances. So we don't normally think of it, but when we're dealing with water, water is a liquid and all the water molecules are all bonded together. Okay? So in order for something to dissolve in water, we need to break the bonds that are occurring between the solid, and we need to break the bonds that are occurring between the water molecules. So we're going to break two sets of bonds and form new bonds. So the process of dissolving is breaking bonds and forming new bonds. It's not forming new materials, it's just breaking bonds between already existing materials. So the bonds between the particles in the solid, which is the solute, are broken as they move away from each other, and we'll talk about that in a little bit more detail in a little while. And the bonds between the liquid particles are disrupted as the solid substance, which is breaking down, moves in between the solute particles. And then you get new bonds being formed between the solute and the solvent. So it's the ability to make bonds between the solute and solvent which will determine whether or not one material will dissolve in a particular, or whether a solute will dissolve in a solvent. So we now can classify the world into two different forms. We've got polar materials and non-polar materials. And the idea is that like dissolves in like. So a polar material will dissolve in a polar solution, a polar solvent. So like dissolves like. So in order for us to dissolve something, we've spoken about the idea that we're breaking all those bonds, requires energy to break bonds. So the stronger the bond, the more energy required, as we would expect. When we form a new bond, energy is released. So the stronger the bond, the stronger the new bond that's formed, the more energy is released. So if we're breaking strong bonds and forming strong bonds, when the strong bonds form and release energy, that released energy can be used to break the bonds between the solute. So if we're dissolving, if we add a solute and a solvent where they have similar strength bonds, then they will dissolve each other. The solvent will dissolve the solute. So if the bonds being broken are similar strength or weaker than the new bonds being formed, then the solute should dissolve the solute. The solute will dissolve in the solvent in that case. So that leaves us with a rule of thumb that polar dissolves polar in most cases. That's a reasonable conclusion. So if we've got some bonds which have got a high bond strength and we're breaking those and forming bonds with a high bond strength and they will release energy. Similarly, if we're forming bonds with a high bond strength, they will, but we're dissolving bonds with a lower bond strength, then that relationship will work as well. So the bonds that are being broken are a similar strength or weaker than the new bonds that are being formed. So here's an example of a table. So miscibility is the ability to be dissolved. So completely miscible tells you that these substances dissolve in water with no problems at all. And then as we go down the table, we get less and less of the material being dissolved until we get completely immiscible. And an example of completely immiscible that you'd be familiar with is oil in water, where the oil doesn't dissolve in the water. So what do we notice about this as we're going down? Decreasing miscibility, yep. What do we notice about so these are alcohols. The OH is telling you that it's an alcohol. We'll deal with alcohols in organic chemistry next year. But we can see, we've got meth eth, prop, bute, pent, which we're familiar with. So methanol is just a methane with a hydroxide on it, which makes it an alcohol. So what's happening as we go down this list?
As the molecules get larger, they become less soluble.
As the molecules become larger, they become less soluble. That's a fair statement based on that. Why do you think that would be the case?
The shape of the molecule, like maybe the surface area between one molecule and the other would vary depending on its shape.
So the surface area of each molecule, so the surface area is certainly increasing as we go down because the molecules are getting larger. So think about intermolecular forces. What's going to be the dominant intermolecular force? Oh, sorry. Is this molecule polar or non-polar? Polar. Will it undergo hydrogen bonding? Why would it undergo hydrogen bonding? Because it's got an O and a H bonded together. The O will have unbonded electron pairs, so it will bond with the hydrogen atom on this oxygen will bond with the unbonded electron pairs on adjacent hydrogens. Adjacent oxygens. So it will have hydrogen bonding occurring. So let's just draw that molecule. So it'll be like that. We've got our unbonded pairs. Well, we've got two unbonded pairs there. So the hydrogen, which will be positive, the oxygen will be partial negative. So when we've got our next molecule, we'll draw it over here, with its oxygen, like that, then this positive will bond there. So we'll get hydrogen bonding occurring there. So the hydrogen bonds that are occurring there will be quite strong, of similar strength to so they're the bonds that would be breaking in order to dissolve that in water. And water has hydrogen bonding as well, similar kind of hydrogen bonds, so the bond strengths will be relatively similar, won't they? What about down here? Would this one have hydrogen bonding? Yeah, that would have hydrogen bonding as well. Do you think the hydrogen bonding here would be as effective as the hydrogen bonding here? No. So what's going to be one of the dominant intermolecular forces that's going to be occurring here? Dispersion forces will be the dominant force here. So what's the relative strength of a dispersion force compared to hydrogen bonding? It's much lower. It's like an order of magnitude lower. So the strength of the bonds being broken here is much lower strength bonds. So when this tries to so to get this to bond with water, there's not very much opportunity to develop hydrogen bonds compared to the size of the molecule. So therefore, as we're going down here, we're getting it harder and harder to dissolve it in water. And we'll see why that is the case here. So in this case here, we've got so what's this? This is 1, 2, 3, 4. So that's butanol. And we can see that we've got our unbonded electron pair with our oxygens. Here's our water molecules with our hydrogen. So we're getting hydrogen bonds occurring here. Okay, so that hydrogen bonding is occurring on this end, but we've got this end here, which doesn't have anything that the hydrogen that the water molecules can bond onto, is there? So there's no hydrogen bonding that's going to occur here. The only type of bonding here with or intermolecular forces that might occur here between this end of the molecule and the water would be dispersion forces, isn't it? Yep, and the dispersion forces are quite weak. So what you effectively do is you can dissolve this end quite easily, but you can't dissolve this end very well. So the more of this chain that you have going on, the harder and harder it becomes to dissolve it. All right, so we've used some terms here, hydrophilic and hydrophobic. Hydrophilic refers to the idea that it's water attracting. It likes water, it dissolves in water. Hydrophobic regions are areas that don't like water and they won't dissolve in the water. So if you've got a hydrophobic molecule, it's going to remain immiscible. If you've got a hydrophilic molecule, it will dissolve. So, to predict our solubility, polar solutes and ionic materials as well, so things like sodium chloride, will dissolve in polar solvents. Non-polar solutes will dissolve in non-polar solvents. So if you have something like, if you had, well, what would be a solid? This is not a so if you had something like oils, they're non-polar. So an oil which is a non-polar will dissolve in another non-polar solvent. So you can clean up oil with kerosene because kerosene will dissolve the oil. So if you get petrol on your hands, for example, when you're filling up your car with fuel, which I'm sure all of you do that for your parents, you've driven me around all the time, I'll pay for your fuel, let me fill up the car for you. And when you fill it up, you get fuel on your hands. When you go to the bathroom to wash your hands, it doesn't come off, does it? When you just wash it in water. Yeah? Because the water, because it's a non-polar material and water is polar, so the polar material doesn't wash off the non-polar. So the solubility of a polar solute and an ionic compound will decrease as the polarity of the solvent decreases. Okay, so that's important. So if we go to more and more so if you go to less and less polar solvents, then it will have less ability to dissolve polar solutes. And as you'd expect, the solubility of non-polar solute increases as the polarity of the solvent decreases. It's kind of a bit of a reverse thing. So sodium chloride will be more soluble in water than in ethanol because water is more polar than ethanol is. So sodium chloride will dissolve better in water than in ethanol. Water would be more soluble in ethanol than in ethoxyethane. Again, because ethanol is more polar, closer to water than what ethoxyethane is. And those of you who watched the video, one of those crash course videos where he gets butter on his hands and tries to wash it off, doesn't wash off because butter is non-polar and water is polar, so it doesn't wash off. But if you've got a non-polar substance, like tetrachloromethane, then it would allow you to wash the butter off because you've got non-polar and non-polar. All right? So acetone is more polar than your tetrachloromethane, and water is much more polar than acetone. So butter will wash off in this, slightly soluble in this, but insoluble in water. Okay? So we'll talk about, I think it will get covered in the presentation, otherwise we'll talk about why you add detergent to your water when you wash up. So you get attractive forces between the ions that you're dissolving. So in this case we've got sodium chloride. The chloride ion here is negative. So the chloride ion attracts the partial positive end of the water molecules in ion dipole attractions. So these are the new bonds that are being formed that release the energy when you're dissolving. So these are the bonds that are being created. So we know that a water molecule has got a partial positive end and a partial negative end. The partial positive end bonds with the negative ion, and the partial negative end, which is the oxygen end, will bond with the positive ions. Okay, so you get these ion dipole bonds or attractions forming in your solution. So the process of dissolving something is pretty much that you get if this is a lattice of sodium chloride where you've got your chloride ions and your sodium ions, the water comes in and you get the attraction between the positive end of the water molecules with the negative ion, which then the attraction there overcomes the attraction with the adjacent positive ions in the lattice, and the water then can take that one away, and then so on the process. As you increase the surface area, you've got a larger surface area for the water molecules to get in there and pull away the individual ions. So if you think about some of the things that help you to dissolve something, if you have greater surface area, you've got more surface area for the water molecules to come in and infiltrate, or for want of a better term, to come in and get around the ions and remove them from the lattice structure. If the water molecules have got more energy, i.e. if they're at a higher temperature, so they're moving around faster, then they'll be able to come in there and dissolve the ion quicker as well. The ionic compound quicker as well. And if you stir it around, which removes these ones that might be hanging around adjacent to this, if you can get those away and bring fresh water molecules in there to remove the next layer of ions, then that process will happen much quicker as well. So we can see that what we end up with is our positive ions surrounded by and bonded to the oxygen end of the water molecule, and our negative ions are bonded to the hydrogen end of the water molecule. And these are the ion dipole attractions that we can see. So they're the new bonds or intermolecular forces that we're generating as a result of dissolving. So we can relate this to, in terms of, we can look at, for example, an ion in solution is surrounded by 6 waters. So this ion complex, as it's known, which has got a +3 charge, so ion can be +3 or +2 charge. In this case, it's a +3 charge. Has 6 water molecules around it, so we refer to the ion complex as ion water 6 because it's got 6 waters. In this case, when we've dissolved cobalt in ammonia, we've got 6 ammonias around the cobalt in this ion complex, and it's 2+. So that's the way we describe it, and we can summarise it like that. So your ion dipole forces don't just occur with water, they can occur with other ones as well. So that ammonia being an example there as well.
So with the H3N and the NH3s, they're different to each other. Is that because of how it connects?
Yeah, so they've just been drawn as H3N to show that the N side is where the negative, partial negative is, and that's what's attracted to the cobalt ion. So the H3N has just got the negative on this side, this has got the negative on that side. So it's drawing it so that the negatives are all facing in. Same as what we've got with the OH2 here. It's just a way of representing for the where the free electrons are. So what you find when you're doing your washing up, which I'm sure that after dinner you will clear the table and say, don't worry Mum, Dad, I'll do the washing up for you tonight, as always. And when you go to wash up, when you try washing up in just hot water with no detergent, the greasy stuff doesn't come off, when you add detergent to it, the greasy stuff comes off. Why do you think that's the case? What do you think that the detergent is doing in this case? Yep. Yep. So it emulsifies the fat. Okay, how does it emulsify the fat? So it breaks down the bonds. Yep.
I'm pretty sure most detergents have a polar end and a non-polar end as well.
Yep.
Polar and non-polar molecules, which means they can dissolve in water and dissolve fat.
Yeah, so they have a polar end and a non-polar end, and what they do is all of the polar ends of the molecules all get together, and they will allow the dissolving of polar grime, grease and dirt and stuff, and all the non-polar ends of the molecules get together, and they can dissolve the non-polar molecules. So what you end up being able to do with what your detergent is designed to do is allow you to dissolve polar and non-polar molecules, and they effectively dissolve in the end of the molecule, which is polar or non-polar, depending upon what the material you're trying to dissolve is. Okay? All right, so that brings us to the end of this section. So we've discussed, right from the very beginning, we discussed the shape of molecules, which is based on the number of electrons, bonds and free electron pairs. We used that to determine the shape of the molecule. We then looked at the polarity of the bonds. We used the polarity of the bonds and the shape of the molecule to work out whether it was a polar or non-polar molecule. We then looked at intermolecular forces, which are caused as a result of the polarity of molecules. So we looked at dipole-dipoles, which occur with polar molecules. We looked at dispersion forces, which occur with all molecules. And we looked at the dispersion forces work better with higher number of electrons or greater surface area, because dispersion forces create instantaneous dipoles. If we've got dispersion forces, if we've got molecules with big surface area, that allows the molecules to come together easier. And if we've got a lot of electrons, that allows the possibility that the randomness of the distribution of the electrons, you've got more electrons to redistribute, the more chance of having a partial positive, partial negative end and create a instantaneous dipole, which increases your dispersion forces. We then looked at the special case of hydrogen nitrogen bonds, hydrogen oxygen bonds, and hydrogen fluorine bonds, and that we know that fluorine, oxygen, and nitrogen are the highest electronegativity elements, so they form very polar bonds with hydrogen. And because hydrogen only has one electron, when it's involved in a polar bond, it really exposes the proton, which means you get a good partial positive charge, and you've got the unbonded electrons in fluorine, oxygen, and nitrogen, which the positively charged partial positive hydrogen can bond to. So that's how we get our hydrogen bonding. We've added to those intermolecular forces the ion dipole forces today, and we've used that to discuss how we can dissolve things. And polar dissolves polar, and non-polar dissolves non-polar, and it's related to the relative strength of the bonds. Okay?